Hello everyone, my name is Chao, and today I'll talk about sort, a new way to think about transactions. A transaction is a very powerful tool for building applications, since it provides four strong properties together packed in a single abstraction, which are atomicity, consistency, isolation, and durability. These so-called ASIC properties allow the developers to treat the entire transaction as a single logical unit, freeing them from worrying about concurrent execution and failures. As a result, programming with transactions is simple and easy to reason about. This is the very reason why transactions became popular in the first place. However, this simplicity comes at a cost of performance. To guarantee isolation, transactions typically need to transactions typically use concurrency control mechanisms such as locks. These mechanisms, as their name suggests, limit the available concurrency and greatly reduce performance when there is contention. In a distributed setting, things are even worse, since transactions typically need to invoke a costly two-phase commit protocol. Concurrency is further reduced because transactions have whole locks for the whole duration of network communication. This is the very reason why this community came up with another approach called BASE. So this approach renounces the transactional guarantees of ACID, instead relying on simple APIs such as put and get in key-value stores. Now, developers can write customer code to squeeze every last bit of concurrency from the applications. Unfortunately, with great power comes great complexity. Without transactional support, now it is up to the developers to provide the consistency guarantees that the application requires. This task is daunting, to say the least, since one needs to reason about all possible interleavings among the operations. Needless to say, this complexity gets out of hand soon, since it increases exponentially with the size of the application. So a daunting-based approach is in fact so daunting and error-prone that more and more developers are rethinking about the trade-off between performance and complexity, and are moving back to the simplicity of ACID transactions. So today, there is a stark choice in front of the developers. They can either choose to live on the deserted island of ACID, where the program is simple, but the performance is limited. Or they can choose to live on the deserted island of BASE, where the performance potential is much higher, but the complexity associated with realizing this potential is prohibitive. These two options, bad as they may be, are the only options available today to the developers. In this talk, I will present sort, a new approach that provides both performance and ease of programming. In our search for this promised land, we draw inspiration from this gentleman. His name is Pareto, and he's famous for the Pareto principle, which says that 20% of the causes account for 80% of the effect. So in computer science, this is more frequently referred to as the 1910 rule. So our experience with a number of applications indeed confirm this principle. We find for most of applications, only a small set of transactions challenging the performance limitation of the ACID transactions. This is because, first, many transactions are not run frequently, such as many administrative transactions. Second, although some transactions run frequently, they are lightweight. They are either small or with low contention and have minimal effect on performance. This observation points us to a potential opportunity. So what if we were able to identify these performance-critical transactions and somehow change them into base style without affecting the rest of them? If we could do it, we would get most performance benefit that base approach can provide while keeping complexity under control. In the rest of the talk, I will tell you how we actually leverage this opportunity. I'll first talk about base transaction, which is a new abstraction we provide for performance-critical transactions. And I will talk about sort isolation, the rule to regulate the behavior between these base transactions and traditional ACID transactions. And then I will talk about how we achieve sort isolation by using locks. Finally, I will quantify the benefit of sort in terms of both performance and ease of programming. So our first goal is to enhance concurrency. A naive way to do it is to break down transactions into smaller ones, providing final granularity of isolation. So here's a transfer transaction which transfer money from one's checking account to their savings account. So this transaction first checks the balance of the checking account. If there is enough money, it deducts the amount of money from the checking account and adds it into the savings account. To bring more concurrency to this transaction, we can break down the transaction into two parts, each part only accessing one account. Concurrency is increased because before this change, multiple instances of this transfer transaction could only run sequentially. But after I break down the transfer transaction, there is more parallelism between these multiple instances of the transaction. So what could possibly go wrong here? Well, imagine there is another balance transaction which tries to correlate the total balance of these two accounts. Before this change, the balance transaction could only observe the states either before or after this transaction. Therefore, the total balance of these two accounts is an invariant. However, after I break down this transfer transaction into two parts, its intermediate state is exposed to the balance transaction. As a result, the balance transaction may observe the invalid state which violates the invariant. This example indicates that providing a final granularity of isolation for even a single transaction may affect the semantic of all transactions. Even others are not modified. So this problem, in fact, is one instance of a general tension between performance and complexity. When we increase the concurrency to get better performance, we also increase the number of interleavings between transactions that the developer needs to reason about, which in turn increases complexity. So the reason why previous approach suffered from this tension is because naively breaking down transactions introduce more interleavings among these transactions and all transactions indiscriminatively. But what if we could introduce more interleavings selectively? More precisely, what if we could only allow this performance-critical transaction interleave with each other, exposing additional states, but somehow hide those states from these non-critical transactions, keeping those transactions unaffected? Coming back to our example, it means we should only introduce more interleavings among these transfer transactions so that instances of this transfer transaction expose their intermediate states to each other. But at the same time, those intermediate states should be hidden from the balance transaction. This way, we can get more concurrency between transfer transactions while keeping the balance transaction unaffected. To achieve this flexibility, we introduce a new abstraction called base transaction. A base transaction consists of a sequence of sub-transactions, which we call alkaline transactions. So you can think of alkaline transactions as small assay transactions. So there are two things that are really nice about base transaction. First, to achieve much of the convenience of assay paradigm, base transactions still provide atomicity and the durability at the granularity of the entire transaction. And second, and more importantly, base transactions introduce more interleavings selectively. So between base transactions, we want more interleaving. So we only provide fine granularity of isolation that span the alkaline transactions. As a result, each alkaline transaction acts as a small assay transaction. These alkaline transactions can interleave with each other, which bring more concurrency. But on the other hand, to assay transactions, base transaction provides coarse granularity of isolation that span the entire transaction. As a result, the assay transaction can only observe the states either before or after the base transaction. This property guarantees that when developers change one transaction from assay to base, it will not affect other assay transactions. So the key reason why base transaction can provide these multiple granularities of isolation, exposing different granularities to acid and base transactions, is a new isolation property we call salt isolation. Salt isolation creates an illusion just like this image. If you tilt your hand to the left, it looks like a duck. If you tilt your hand to the right, it looks like a rabbit. So salt isolation plays a similar trick here. So it ensures that base transactions, when seen by other base transactions, looks like a sequence of small assay transactions. However, to ACID transactions, they look like a single monolithic ACID transaction. This duality is the key to achieving good performance while keeping complexity under control. Now, let's see how we actually achieve this illusion of sort isolation. Our current implementation relies on a single mechanism, logs. We focus on a log-based implementation because we are targeting the workloads with high contention, and logs are well suited for this type of workloads. So transactional databases use a single type of logs, let's call them ACID logs, to isolate ACID transactions from each other. In contrast, here, in order to provide multiple granularities of isolation, sort introduced two new types of logs, alkaline logs and SALINE logs, that allow base transactions to look both as dogs and as rabbits. We all know how ACID logs work. When this ACID transaction updates X, it acquires write lock on X and holds it until the end of this transaction. If there is another transaction that tries to read X, to get the read lock on X, it has to wait until the end of this read transaction. More formally, the behavior of ACID logs is captured by this log table, which shows that ACID logs conflict with other ACID logs except when both of them are read logs. Base transactions, however, are different. They have to sustain multiple granularities of isolation. Consider this base transaction. Suppose the first alkaline transaction updates X. If there is another base transaction that tries to read X, it has to wait until the end of this alkaline transaction. If there is no further conflicts, then the green base transaction should be allowed to execute concurrently with the remaining alkaline transactions. However, if the transaction that tries to read X is an ACID, it is not enough to wait until the end of this alkaline transaction. Remember that sort isolation requires that to ACID transactions, a base transaction looks like a single monolithic transaction. As a result, this ACID transaction has to wait until the end of the entire base transaction. This is where the new types of logs come to the fore. We introduce alkaline logs to protect alkaline transactions from both ACID and base transactions. And we use SALINE logs to protect the rest of base transactions from ACID transactions. Let's look at these new logs in a little more detail. First, alkaline logs. The mission of alkaline logs is to protect alkaline transactions from both ACID and base transactions. So the alkaline log should conflict with both ACID logs and alkaline logs. As a result, the extended log table looks just like the original ACID log table. All ACID and alkaline logs conflict with each other unless both of them are read logs. But how to protect the states that generated after the base transaction, after the alkaline transaction commits? Well, in sort, after the alkaline transaction commits, we downgrade the alkaline log to a SALINE log. The mission of SALINE log is to protect is to make such states invisible to ACID transactions, but accessible to base transactions. That's why SALINE log only conflict with ACID logs, but are compatible with both SALINE log and alkaline log. So, are we out of the woods now? Not quite. So, even with this log design, there is still a subtle case that an ACID transaction may observe an intermediate state of a base transaction. Here is an example how this could happen. It all starts when the read base transaction updates X, which is then read by another base transaction. That base transaction propagates the value of X to another variable Y, which is then read by an ACID transaction. In this case, the ACID transaction in fact observes the intermediate state of the read base transaction indirectly. The source of the problem is that the log conflict table only defines the behavior between two transactions. But since we do not always fully isolate base transaction, a base transaction may affect another ACID transaction indirectly. In our paper, we provide a simple and efficient solution to this problem, which is one of the main joys we will have by reading our paper. The bottom line here is that sort prevents all acid transactions from being affected by base transactions, either directly or indirectly, in all log-based isolation levels. So in our paper, we provide a theorem that formally states this guarantee, and we provide corresponding proofs. But how does sort perform in practice? To answer this question, we have implemented our sort prototype on top of MySQL cluster to demonstrate the performance gain we get and engineering effort sort requires. So sort is predicated on the claim that it is possible to get most of the performance of base while retaining most of the simplicity of acid. Our evaluation is try to verify the validity of this claim by answering two questions. First, if we just basify a few transactions, what is the performance benefit over acid? Second, can we get most performance of base while only requiring a small fraction of programming effort? We run our experiments in a configuration of 10 shards with 3 replicas each on Utah EmuLab. We use 3 workloads to evaluate our prototype. We first use TPCC, which is a popular database benchmark modeling online transaction processing. And second, to get experience on real applications, we also use Fusion Ticket, which is an online ticket selling application. In addition, we run several micro benchmarks to demonstrate the performance of sort under different conditions. In this talk, I'll only show the results of a Fusion Ticket application. To answer the first question, we use the throughput latency graph of a Fusion Ticket application, using both the acid and sort approach. In this experiment, we changed just one transaction for sort approach by modifying 15 lines of code. This change took us 15 man-hours without prior familiarity with the code base. As shown in this graph, sort approach can achieve a throughput at 7,000 transactions per second, which is 6.5 times higher than acid. You may notice that when the throughput is lower, the latency of sort is higher. This is because this acid approach is run on top of MySQL cluster, which in fact renounces the durability guarantee. MySQL cluster only log to disks asynchronously. But instead, in our prototype, in order to provide durability, base transaction log to disk asynchronously, which results the increased latency. To answer the second question, we perform an experiment to help us understand how close we can come to the performance of pure base approach. As I mentioned before, by basifying a single transaction, we get a speed up of 6.5 over acid. As shown in this graph, by basifying the next 1 or 2 transactions, we do not get additional performance benefit. But what if we basify more transactions? But as I mentioned, the complexity increases exponentially, and there are 11 transactions in the Fusion Ticket workloads. It is very hard for us to basify all of them. Instead, what we do is we just break down the transaction to row operation. Of course, this implementation do not provide any semantic guarantees, but it simply gives us a sense of the upper bound of the performance that pure-based approach can achieve. What is remarkable here is that by basifying a single transaction, we can achieve more than 19% of the performance benefit that pure-based approach gives us. Of course, sorts was not born in vacuum. There has been work on the acid side to optimize the performance of acid transactions, and there has been work on the base side to provide stronger semantics. Sort is the first work to combine, in a meaningful way, the benefit of both acid and sort approach. In conclusion, sort overcomes the sterile acid-base dualism by revisiting the abstraction of transaction in a fundamental way. Traditional transactions try to provide all acid properties at the same level of granularity. Instead, base transactions try to decouple the granularity of isolation from that of other properties and provide multiple granularities of isolation. This is the key insight why sort can achieve most performance of base while retaining most of the simplicity of acid. Thank you.
Marcos Aguilar. I was wondering if you have guidelines for the developer to choose between the two types of transactions. At the end of the day, you probably want to satisfy invariance on your data, and you're given like 10 different types of transactions. How should the developer decide, oh, no, this is going to be ACID, this is going to be based?
Okay. So in fact, theoretically, we want to find the transaction we want to find the large transaction with high contention. This is what we want to find. But in fact, practically, it's very easy to find. Here's an example. So this is how we find the transaction in TPCC benchmark. So we just increase the workloads of the TPCC. As you see, the latency of the performance critical transaction increase much faster compared to others. So this, in fact, this graph points out that the base payment transaction is the first one we should basify because it, this graph shows the payment transaction is a contention bottleneck of the workloads.
But that's just performance-wise, right? You want to know about your data invariance. How do you know that replication remains correct if you basify a given transaction?
Okay, so for this is the second question. The question is like, if I basify a transaction, how could I make sure this is a correct one, right? Is this a question?
Yeah, that's the question.
Okay. So there is like some availability. So some responsibility is the developer should should make sure something. So basically, it's like developers should need to make sure the interleaving of base transaction results a consistent state. But sort isolation helps you to help you to free worry about the interleaving between base transaction and the ACID transaction. But the developer need to make sure the interleaving of base transaction should not result in inconsistent state.
Henry, Stanford University. Can you go back to the slide with the latency and throughput?
Sure.
And great talk, by the way.
Thank you. This one?
Yes. Just curious about where you're getting these points where the throughput is basically constant, but the latency seems to be going upward, like vertically. Are these individual experimental points, or are these aggregates?
No, because at this time the it's already the bottleneck of the. So you satisfy the system already. So when I add more clients, the latency will become higher, but the throughput will stay the same because you have more clients.
So the individual points represent numbers of clients?
Yes.
Oh, thank you.
We'll take two more quick questions.
Hi. Yang Zhang from New York University. I want to ask that your system has locks. So how do you handle data locks?
So we implemented on top of MySQL cluster. The MySQL cluster only use timeout to detect the data lock and roll back one of them.
Okay, so the problem is if you are using early commit in the base transactions. So if base transactions commits early and release its data to other base transactions, and it aborts later because of data lock detection, then what are the other base transactions going to do?
So for the atomicity, we follow the same techniques like transaction chains. So the base transaction can only abort at the first alkaline transaction. After it cannot abort. But we provide the exception handler. If there is something wrong, we can throw exception to the developers, and you can handle it.
One last question.
Sure.
Dave Anderson, Carnegie Mellon. I'll try to keep it quick, but it's a little long. So I wanted to think about this in the context of two other trends we're seeing, which is you said a lot of things about the developer must X and the developer must Y, and they've got to juggle their acids and their bases and their salts and their solutions and mix their vinegar and baking soda appropriately to achieve volcanoes. When you look at something like Google, right, Spanner is an evolution of a system that used to not provide strong consistency. And one of the motivating things there was that in order to harness an army of 20,000 programmers, you actually want it to be easy for them to program. And then you've got things like HStore coming in, which you mentioned but didn't discuss, which say, you know, simplicity is awesome. Let's not worry about all of this concurrency. Let's throw it all away, and we will achieve transaction rates that are an order of magnitude higher than what you show in your paper for TPCC. And so you've introduced complexity and programmer demand in order to give me something. And I'm curious, in 10 years, are we going to look back and say, thank God you gave me the flexibility to do this because it solves my problem? And if so, I want to know what problem it is you have in mind. Or, whoa, remember those bad days when we thought that all that complexity was necessary when we can just run this on one big server?
So I will answer the question in two parts. The first part is like, there's a bunch of related work try to increase the concurrency of ACID transactions. They can divide it basically into two types. The first type is try to optimize the specific type of transaction. The second type is try to optimize the general transaction, but you need to satisfy the certain condition. So sorting instead is more general applicable. So this is the first part of the answer. The second part is like, in fact, by our experience, most of the time the BASE-ifying transaction is pretty simple because the reason is that previously we only provided a single level isolation to describe the isolation the application wants. In fact, here we provide multiple granularities isolation. It's very natural it's more precisely to describe, it's a more precise way to describe the isolation the application wants. And I think, so so I also show like for the Fusion Ticket application, we only modify 15 lines of code out of many lines of code. So I think the change by our experience is not very complex.
Great. On that note, that's a very long discussion. Let's take the rest of the discussion.
Thank you.
Thank you.